So we're going to continue this series of lessons on waves and vibration. This is part 3. And we have 2 main topics that we're going to look at. The first is to describe the Doppler effect, what causes it, and identify some applications, as well as we'll solve some numerical problems around this concept. And then the second is we're going to have some fun looking at how a shock wave, or sometimes referred to as a sonic boom, is created. All right, so let's talk about the Doppler effect. So listen carefully, right? We've all heard this phenomena before when we're standing beside the road and we hear a car pass, its horn is blasting, or perhaps maybe a public safety car, police car, or ambulance with its siren going on. So it sounds something like this. So notice as we hear this car pass, 2 things happen. One, it certainly gets louder as it gets closer to us, and then softer as it drives away. But we also hear the shift in the pitch or frequency. It seems to be a higher pitch as it's approaching us, and then as it passes us, we hear it kind of shift down to a lower pitch or lower tone or frequency. So what causes that? Well, let's look at a couple cases here. The first is if we have a sound source, say a speaker, that is stationary, and our ear is stationary as well, no matter what position we would place our ear in around that sound source, we would hear the same frequency. Notice the waves propagate or move out from the sound source in the center at a uniform frequency, and the frequency or wavelength is represented by the spacing between these circles as they pass out. It's kind of like you throw a pebble into a still pond and you see the waves or ripple propagate out from that point. So the closer the lines, the shorter the wavelength and the higher the frequency. Okay, now what happens if that sound source is moving towards us? Notice the wavelength or the sound waves tend to get pushed together on the side that's moving towards us, because the source is moving in the same direction that the sound waves are propagating out. So what does that sound like to the ear? Well, the shorter the wavelength, the higher the frequency. Okay, so we would hear a higher pitched signal if the sound source is moving towards us. Now, if the sound source is moving away from us, then the wavelength gets stretched out, and that longer wavelength means a lower frequency or pitch. So when an object is moving away from us, the tone of that sound, or the frequency of that sound, will appear to be lower in terms of how we observe it. So this is what we call the Doppler effect. It's the shift in frequency that occurs as a sound source is moving either towards us or away from us. So let's look at a short little video that does a good job of describing this. It turns out this applies not just to sound waves, but also to light waves.
Fun science, fun science, fun science, it's a science of fun, yeah. Today I'd like to tell you some cool things about light! Now, as I'm sure you're aware, the speed of light is 299,792,458 meters per second, which is pretty bloomin' fast. To give you an idea as to how fast that actually is, it would take a beam of light 1.255 seconds to travel from the Earth to the Moon. The speed of sound is only 340 meters per second, which is still pretty fast, even though, thanks to science, humans have managed to go faster than that. But if you want to go faster than light, then sorry, you can't. It's not possible. It's theoretically possible that we could one day travel very, very nearly almost as fast as light, but to go faster than that's... no, sorry. Now, before I can tell you about all of the really cool stuff that comes with light and the speed of light, I have to tell you about this other thing called the Doppler effect, which is still really interesting, so, you know, don't leave just yet. The Doppler effect is the change that you notice in the frequency of a wave when the source of that wave is moving relative to you. For example, imagine that you're sitting by a canal enjoying the lovely British weather when suddenly... I appear next to you screaming like a lunatic. From your perspective, it's just really, really weird. However, if theoretically I wasn't standing next to you but was running past you at 80 miles an hour, still screaming just as I was before, as I approach you, the pitch of my scream would be higher, and then as I pass and run away from you, the pitch of my scream would drop, even though from my perspective, I'm screaming at exactly the same pitch as I was when I was standing still. The reason this shift in pitch happens is because when I'm sitting still and screaming, ah, the sound waves are emitting from my mouth uniformly. But when I start moving, the sound waves in front of me get squished up and the sound waves behind me get stretched out. And it's this change in the frequency that causes the change in pitch as I pass, and that is what the Doppler effect is. The reason the Doppler effect is important is because it doesn't just apply to sound, but it also applies to light. Bet you didn't see that one coming, because it's not a video about light or anything like that, is it? Oh. So just as when something is moving and emitting sound, you can hear a difference in the pitch of that sound, when something is moving and emitting or reflecting light, you can see a difference in the colour of that light. For example, imagine that we're in exactly the same running canal situation as before, except this time I'm not screaming like a lunatic, and instead of running at 80 miles an hour, I'm running at very, very nearly almost the speed of light. What would you see? Well, you probably wouldn't see anything at all, because as you'll remember, the speed of light is very, very, very fast, and I'd be gone before you even knew I was there. But let's pretend that you had a magic iPhone app that would let you take pictures of me travelling very nearly at the speed of light. What would you see? Well, when I'm running towards you, the light in front of me gets squished, and the frequency of that light gets shifted to the blue end of the visible light spectrum, and so I appear blue. And then as you see me running away from you, the same thing happens in reverse. The light behind me gets stretched out, shifts to the red end of the spectrum, and then I appear to be slightly red. Now this change in the frequency of light is something that happens all the time. In fact, it's happening right now as I move forwards and backwards from you, but the change is so negligible that you can't notice it unless something is travelling at very, very nearly the speed of light. But easily the coolest thing that happens when you travel at very, very nearly almost the speed of light is that when you do, time slows down. All clocks, whether man-made or biological like me, tick slower when you're travelling that fast. So back to our thought experiment where I have the ability to run very nearly at the speed of light. Imagine that I decided to take a couple of minute tour around London travelling that fast. Well, it might have only seemed like a couple of minutes to me, but to you, travelling at normal human speed, it would have been many, many years. And so by the time I returned from my very short run, you would have died of old age. And that, ladies and gentlemen, is light. This is the end. Bye.
You've just had the almost imponderable joy of watching Charlie Is So Cool-like, which makes you like cool.
Okay, so a little fun there with Charlie, but a great example of both how the Doppler effect applies to sound, but also to light. So let's look at a couple applications of the Doppler effect. One is with police radar guns. So hopefully you have not experienced this personally in your driving histories, but they use a radar gun that utilizes the Doppler effect to measure the speed of cars on the road. Now, how does it work? So the radar waves are electromagnetic waves, basically the same type of waves that make up visible light. It's just at a different frequency, a radio wave that we can't visibly see. So that wave travels out. Now, when it hits the car, it's going to reflect back. And if the car were at rest, it would reflect back with the same wavelength. But if the car is moving towards the gun, they're going to move back at a shorter wavelength or a higher frequency. So the radar gun is designed to know what frequency it sends the wave out at, and then it measures the frequency that it gets reflected back. And the change in that frequency can be used to compute how fast the car is moving. So that's basically how radar guns work. They work on the basis of this Doppler effect. An application in terms of visible light and how it's affected by the Doppler effect has to do with its shift, right, to either blue or red, as we saw in the video. So remember, blue has shorter wavelengths or higher frequency, and red light has a longer wavelength or lower frequency. So as a light source is moving towards us, it will have a shorter wavelength and therefore shift in the blue direction. If it's moving away from us, it will have a longer wavelength and shift in the red direction. Now, one of the neat applications of that is that astronomers actually use the Doppler effect to determine the velocity of stars and the presence of planets. So they can sometimes determine how fast a star is moving and whether it's moving away from us or towards us based on the shift they see in the frequency or color of the light. They can also detect if the star is wobbling. Now, remember, we talked about circular motion, and when you have other planets around the solar system, it can cause that whole solar system to wobble due to the effects of gravity. So they can detect that wobbling by some points in the orbit of the solar system, the sun is moving towards us, right? And that would give us a blue shift. And then we see it move away from us, that's a red shift. So if they observe this over time, they can tell how much is it wobbling and potentially can determine indirectly, are there planets orbiting around the sun, even the extent to maybe the size of the planet, the mass of the planet, and how often it orbits the sun. So lots of really neat effects or applications of the Doppler effect. All right, so let's formally define this, and let's look at a formula, apply a little math to the Doppler effect here. So it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. So formula looks a little messy, but let's just break it down here. So what we're use this to solve for is what would be the shifted frequency, the Doppler frequency. So that's F sub D. And we calculate that by starting with the source frequency. What's the frequency of the original source? This would be the same as what is the frequency we would hear or detect if it were stationary at rest. And then we multiply that by this ratio. And the top is the difference between the speed of sound. So for most problems, we're going to use 340 meters per second. That's kind of the typical speed of sound through air at normal temperatures. So the speed of sound minus the speed of the detector. So that would be you, the listener, right? Are you moving at a speed away or towards the sound source? And then that's divided by, again, the speed of sound minus, and this time the speed of the source. So this is the car. Is it moving towards us or away from us, and how fast? So that will give us the Doppler shift. So let's label a few things in our picture here, right? The horn on the car would be the frequency source or source frequency. The ear listening would be the detected frequency that we hear. Big V, right, is the speed of sound. V sub S is the speed at which the source of the car is moving towards us. And V sub D would be the velocity or speed at which the detector is moving. All right, let's put an example in place here. So it says a car is traveling towards you as you stand still, honking its horn at 500 hertz. The car is traveling at 50 meters per second. What frequency will you hear? And we're going to use a 343, a little more precise measure for the speed of sound through air. So what do we know? Well, before we do that, actually, it's really important on these problems to define what is the positive direction, right? Because the speed of sound, we're going to treat it as a velocity. It has both a magnitude and a direction. And when we put it into our formula, it's really important to know whether we treat these velocities as positive or negative. So we're going to define positive as the direction that the sound wave has to take to reach the detector. So in our example here, if the car is moving to the right, what really matters is that the sound waves have to travel from the left to the right to reach the detector. So we're going to call that direction positive. You see, I put this plus over here to the right and a negative to the left. So that will help us to assign positive or negative values to the source and detector velocities. All right, so what do we know? We know the speed of sound is 343. We know the source velocity. It tells us the car is moving towards us at 50 meters per second. So notice the car is moving in the positive velocity direction. So we're going to keep that value positive. We're standing still, so our velocity is 0. And we know the source frequency is 500. So what are we trying to solve for? We're trying to solve for the Doppler frequency. So let's just plug it into the equation. So we have our source at 500 hertz. We have 343 minus 0 because the detector, our listener, is at rest. And then divide that by 343 minus 50. Now notice the equation up in the top right-hand corner, it's the velocity of sound minus the source velocity. And since our source velocity is positive, but the formula has a subtraction in there, we're going to keep the negative sign in there. All right, so if we do all the math, do that on your calculator, we would see that the Doppler frequency would be shifted upwards to about 585 hertz. And that makes sense. We know the sound source is moving towards us, so it should shift to a shorter wavelength and a higher frequency. All right, let's look at another example. This time the car is moving away from us. Everything else is the same, right? So which way are we going to call positive? Well, even though the car is moving to the right, the sound, in order to reach the detector, is moving to the left. So we're going to call the left direction the positive direction in this example. So here's our speed of sound, 343. That will always be considered positive. The source velocity, the car is moving away from us. So we're going to treat that, notice, as a negative 50. And then the detector is 0, and the source frequency is 500. So we plug all that in, and this time we should get an answer that's below 500, right? Because as the sound source moves away, we should get a lower frequency shift. And indeed we do. We would detect or hear a frequency of 436 hertz as that car moves away from us at 50 meters per second. Okay, so that's the Doppler effect. The assignment today will have some concept questions with this, but we'll also have a few that we're going to apply the formula here and do the math and figure out what the Doppler frequency would be. All right, the next concept we're going to look at is a bow wave, or sometimes called a shock wave. And it's created when a source, let's say the source is this jet airplane here, equals or exceeds the speed of the sound wave. Now, if it just matches the speed of the sound wave, then the pressure waves that are generated by the nose cone of the airplane are going to basically stack up on the right-hand side, right? Because the waves will kind of pile up, and that piling up of waves, if you think of the circles here as being a high pressure or maximum pressure area of the sound wave, you're going to get a buildup of a high pressure zone there. And that is what you hear as the sonic boom when that high pressure wave passes your ears, this stacking up of sound waves because the source is equal to or greater than the speed of sound. Now, really early in the jet age, right, they thought the sound barrier might be something that could not be broken, but some of the early experimental aircraft proved that we could do that, and we do that on a routine basis now today, particularly with military aircraft. Now let's look at it again, where we're flying actually faster than the speed of sound. And when that happens, we actually create a shock wave that is in the shape of a three-dimensional cone. Okay, so think of like a traffic cone, an orange traffic cone, but on its side here. So you have this high pressure area that's on the surface of this traffic cone. And anywhere that that surface of the traffic cone passes your ear, that's where we hear this very loud, distinct sonic boom. or sometimes we call it sonic boom, but the correct physics word would be a shock wave. So let's watch a little video that explains this a little bit, but shows some really great examples of this. It turns out that when this pressure wave is created, because of the pressure differential, very high pressure on the cone itself and then lower pressure inside the cone, if there's any moisture in the air, that moisture will condense inside the cone. So you get this great visual that allows you to actually see what this pressure cone or shock wave looks like coming off of the airplane.
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it. Going close to that speed through air can cause some unusual visual effects. What you're looking at here is a NASA image of an SR-71 bending light waves from the pressure differentials it's producing. Air's pressure and temperature both drop when airspeed increases. Rapid changes in density can be enough to bend light like a lens. How does it happen? Airspeed increases as it flows over the form of an aircraft pushing its way near Mach 1, the speed of sound. That means that even aircraft slower than the speed of sound can accelerate the air moving over them beyond the speed of sound. As pressure all around the aircraft drops, that air cools. And as air cools, its ability to hold moisture drops. So if there's enough moisture, you'll see it form in clouds that appear attached to the aircraft itself. But the cone-shaped clouds you see aren't in fact traveling with the aircraft. Each section of air is spontaneously reacting to the temperature and pressure change induced by the aircraft's body sliding past. Then there are the shock waves. Shock waves are formed by the air that can't get out of the way fast enough, forming a pressure wave. We perceive that pressure wave as sound. Aircraft actually usually produce two booms. They just reach us so quickly in succession that we can't distinguish the two. All of these factors are quite normal and have come to be expected in images that capture supersonic, transonic, or even near supersonic flight. But on rare occasions, we do get a glimpse of something special. At Kennedy Space Center on February 11, 2010, an Atlas rocket launched into ideal conditions for showing off shockwave. And this is the result. We hope you've enjoyed this little tour of visual and auditory speed of sound phenomena. Visit avweb.com for aviation news and inside information for pilots. This has been Glenn Pugh for avweb.com. Thanks for watching.
All right, so pretty cool video there. And those videos of the Blue Angel jet flying over water, that was right here in San Francisco Bay during Fleet Week, perhaps. Some of you have gone down and watched the Blue Angels perform, pretty cool. So we can do some modeling of how this shock wave behaves by using a diagram like that is shown here on the slide. And what this is showing is the shape of the cone or shock wave, but clearly we're just looking at it in 2 dimensions. In reality, it's a 3-dimensional wave. And the location of that shock wave, as well as the location of the airplane. Okay, so the shock wave is going to form around the airplane itself as it travels. So at time equals 0, the initial wave and the plane are in the same location. But notice what happens. At 1 second, the circle represents how far the sound wave has moved during that 1 second time period. And notice the airplane has traveled about twice as far ahead as the sound wave has, twice as far as the circle. And we see that continues, right? At 2 seconds, sound wave travels further, but the airplane itself continues to travel at twice the distance, and the same thing at 3 seconds. So we can model not only this shock wave, but also use it to illustrate the speed at which the airplane is traveling compared to the speed of sound. Now, we call that the Mach number. It's the ratio of the aircraft speed to the speed of sound. You probably heard this. Planes that are flying at Mach 1 or Mach 2. So Mach 3, for example, would be 3 times the speed of sound. So if we take 340 meters per second as the speed of sound, Mach 3 would just be another way of saying it's traveling at about 1,020 meters per second. Now, Mach 3 is pretty fast. That's maybe just some of the highest performance military aircraft that we have that can fly at those speeds. But most of our jet fighters can easily fly at close to Mach 2 or slightly over Mach 2 in their speed. So again, we talked about what this circle is. A circle represents the propagation of the sound wave, and we can see how much faster the plane is moving compared to the sound wave. So let's take this last picture down here and compare the distance between our kind of zero reference point, the center of the circle, and how far the sound has moved in that time period versus how far the airplane has moved in that same time period itself. So the distance from 0 to B, which is the distance the plane has traveled, is twice as far as the distance from 0 to A. So based on this diagram, we would say that the jet is traveling at twice the speed of sound, or we could describe it as Mach 2. So these types of diagrams will allow us to determine how fast is the plane traveling. Now, I'll pose this question, but we'll explore it more in the assignment today. As the plane goes faster and faster, what happens to the shape of the cone or this sound wave, right, that's shown here drawn on the airplane? Would it get narrower and pointier, or would it get wider and kind of stubbier as the airplane goes faster and faster than the speed of sound? All right, so that's what we're going to talk about today. We've described the Doppler effect and some of its applications, and we even have an equation we can use to determine the actual Doppler frequency. And we understand conceptually how a shock wave is generated. And we have some kind of a graphical tool we can use to represent how fast an airplane is traveling compared to the speed of sound.